Welcome to this class on Abstract Algebra. In this class, we are going to learn the definition of a group, which is the starting point to learn the Abstract Algebra. Before going to learn the definition of a group, first we need to recollect some of the important and fundamental number systems which we have learned in our earlier school days or college days. Let us go into details. The first and foremost number system is set of all natural numbers, which contains 1, 2, 3, 4, 5, 6 and so on, all the ordinary numbers. And adding 0 to the set of natural numbers, we get the set of all whole numbers. And coming to the set of integers, which contains both positive numbers, negative numbers and 0 also. Coming to rational numbers, which are numbers of the form p by q, where q is not equal to 0. So this contains set of all fractions in which the denominator is not equal to 0. And coming to the irrational numbers, real number system includes both rational and irrational numbers. And there are Gaussian integers which are of the form a plus ib, such that a comma b belongs to z. And there are complex numbers which are of the form a plus ib, such that a comma b belongs to r. These number systems are used in our coming problems. So for reference, they are given here. The things that we are going to discuss in this class are: what is a binary operation, what is a closed property, what is mean by associative property, what is identity property, what is inverse property, what is a commutative property, and what is a group. All these things we discuss in this class. First, we have a look into the first thing, what is a binary operation. The binary operation, as the name binary indicates, by means 2, we all know it. So definitely we use two numbers in binary operation, and finally we are getting a single element. So let us see those details. For this, we consider a non-empty set S. S is a non-empty set here, and then we find S cross S. You know what is S cross S? S cross S is a Cartesian product defined from S to S. It contains set of all ordered pairs. So we define a mapping F from S cross S to S, that is S cross S contains set of all ordered pairs and S is a set, and we define a mapping from S cross S to S. So like that, every element of S cross S, that is every ordered pair, is mapped to some other element of S. So F is defined in such a way that every element, or that means element of S cross S means ordered pair. So ordered pair of S cross S is mapped to some other element of S. Then that too, one more thing, it should be done in a unique way. Every pair of elements of the set S cross S is related with a unique element of S. Then we say that this F is a binary operation, also otherwise called a binary composition. So if you observe the carefully binary term, we are taking two elements in the form of ordered pair, and we are getting a single element. So that's why it's called a binary operation. So moving on to the next item, what is a closed property? Just we have seen that if a comma b are elements of S, then a circle b, here circle is called a one operation. It's an operation. So we have four fundamental operations in mathematics. One is, we call them as addition, subtraction, multiplication and division. Circle is just like that, one operation, and it can be defined in our own way, by our own choice. Generally we come across that a circle b can be defined as a plus b minus ab, like that. This is one definition. Or otherwise we can define a circle b like a plus b, a plus B, like that. We can define A circle B in our own way, where A, B are elements of some Z or N or W or Q, whatever may be the set. We can choose any choice of definition of A circle B. Circle is like such definition. If A comma B are elements of S, then A circle B is also an element of S. This may not happen all the times. If A, B are elements of S, A circle B may not be an element of S. But if this happens, then we say that the circle is a binary composition or binary operation, and this whole property is called closure property. So in this case we say that S satisfies closure property with respect to the operation circle. Let us see one example to understand this clearly. Suppose we take this set Z. You know, Z is a set of all integers, and I am considering 1 comma 3 belongs to Z, and addition as the operation. If we add these two things, 1 plus 3 is equal to 4, which is clearly an element of Z. So we have taken two elements A1 comma 3 in Z, and we are adding these two things. Finally the result is also belonging of Z. So this is just like one application of this closure property. So we are taking A comma B belongs to S, A circle B also belongs to S. That is the original definition. Here 1 comma 3 belongs to Z, and 1 plus 3 also an element of Z. So here in this case we say that this operation is a binary operation, and we say that this property, this closure property is satisfied in Z with respect to the operation plus. This is one example about closure property, and just we move on to the next property, associative property. To use associative property, we need to select three elements, A comma B comma C. In this property, what we do is we just perform the operation between first two elements and again with the third element. We change the order. We perform the operation between B and C, and again A with the previous result. If we get both the results are same, if we get the same results in all the two cases, we say that this associative property is said to be satisfied in this set S. A circle B circle C must be equal to A circle B circle C. So whatever may be the order we are taking, the answer must be the same if we does not change the order of the elements. We just change the bracket, still we are getting the same result. So that is the essence of this associative property. For this also we take one example. For example, take set of integers 2, 4, 1, they clearly are the elements of Z, and we am taking the multiplication as the operation denoted by dot. So now I am taking in this way 2 dot 4 dot 1, that is 4 1s are 4, 4 2s are 8, 8 is the answer. Here just we change the brackets, 2 dot 4, that is 2 into 4 8, 8 into 1 1, here also getting the same answer, 8 equal to 8. So even after we change the brackets, we are getting the same result. So we say that associative property is satisfied in Z with respect to the operation multiplication. Just by taking the ordinary multiplication, we observed that associative property is satisfied in Z. Likewise, we can prove in any set also. Coming on to identity property. As the word identity indicates, identity means reflecting yourselves. If you stand before the mirror, generally what we observe your image, not the other people. So you are your identity. You are getting your identity if you stand before a mirror. Just like here also, there is an element A, there is element E. If we operate E on A, again you get A. That is, we are getting its identity. There is element E and there is element A. If you perform E on A, again you get A. That is, we are getting the same element. That is called the identity property, and in this case this E is called the identity element. So A circle E is equal to A, and again E circle A is also equal to A. Here this E is called the right identity and this E is called the left identity. Generally these two must be equal. So coming to the definition, let S be a non-empty set and circle be a binary operation. Yes, if there exists an element E such that A circle E is equal to E circle A is equal to A, for each A belongs to S, then this E is called the identity element of S. Here one thing we should observe, identity element changes with the operation. It may not be the same for all the operations in the same set. Even if you take the same set, if you change the operation, the identity element also changes. Let us see. For example, if you take W, the set of all whole numbers, 4 is an element of W. 4 when added to 0 gives 4. This 0 is called the identity element here. Because we are using the operation addition, this 0 can be described as the additive identity or otherwise called identity element with respect to addition. So if we take the set of all natural numbers, for example, if we take 4 and consider the operation as the multiplication, 4 multiplied by something is equal to 4. What is this something? This must be 1 because 4 ones are 4. Here this 1 is called the identity element with respect to multiplication in n, otherwise called multiplicative identity in n. So this is just like A circle E is equal to E circle A is equal to A. Here also A circle E is equal to E circle A is equal to A. Here the operation varies, but the structure is same. This is just like A circle E is equal to E circle A is equal to A. Here also A circle E is equal to E circle A is equal to A. Here E is 0, here E is 1. So that is all about identity property. Coming to the inverse property means we take two elements A comma B, we apply operation between these two elements, finally we get the identity element E. That is the essence of this property. If you perform the operation between two elements A and B, finally you have to get the identity element. A circle B is equal to E or B circle A also is equal to E. In this case, we say that this B is the inverse of A and we denote it as B is equal to A inverse. B is equal to A inverse. Suppose I am taking Z as the non-empty set. Z means set of all integers which contains both positive numbers, negative numbers along with 0 also. Suppose 3 is an element of Z and I am taking multiplication as the operation. Suppose 3 into 1 by 3 is equal to 1. As you know, 3 multiplied by something is equal to 1. Therefore, generally this 1 by 3 is the inverse of 3. 1 by 3 is the inverse of 3. But the thing is that this element is definitely an element of Z. This element, the inverse element that we are calling, it must be an element of Z. But we can observe that clearly 1 by 3 is not an element of Z. Therefore, we say that Z has no multiplicative inverse. Z has no multiplicative inverse. If we change this set, if we take Q, rational numbers, clearly 1 by 3 is an element of rational number. Clearly it is a rational number. Therefore, in Q, it clicks. Q has multiplicative inverse for 3. But in Z has no multiplicative inverse. Like that, this element must also be a member of the given set. Then only we say that this inverse property exists or satisfied. Clearly, if we consider the usual multiplication as the operation, we can easily identify that 1 is the multiplicative identity. So finally, we conclude that 1 by 3 is the multiplicative inverse of 3 in S. 3. S means here that is Z. But we also observed that Z has no multiplicative inverse for 3. Whereas in the case of for Q 3 has multiplicative inverse because 1 by 3 is a member of Q. Like that, we can observe all these things. And here I am giving you some kind of activity. We have seen all the four properties called closure, associative, identity, inverse, closure, associative, identity, inverse, and we have seen some sets n, w, z, q, r, natural numbers, whole numbers, integers, rational numbers, and real numbers. See here the table. In this table, first you take plus as the operation, and you have to put yes or no in these columns. For example, I am giving you three classwork. For if you take n, the set of all natural numbers, and if you take the operation as plus, you test closure property. That is, if you take two elements, that is for example 2 comma 3 belongs to n, then apply the operation 2 plus 3 is equal to 5. 5 also an element of n. Therefore, closure property is satisfied in n with respect to plus. So, write yes. For example, if you take z, I am testing the identity property with respect to the same operation. Perform all these things with the only operation as addition. So, I am taking z and identity element we are testing. In z, if you take an element, for example 4 plus something is equal to 4. Again, identity means, as already said, we have to get the same element. So 4 plus something is equal to 4. What is that something? That something is 0. So 4 plus 0 is equal to 4. 4 plus 0 is equal to 4. Is equal to 4. That means we can easily observe that this 0 is the identity element in Z with respect to addition, and clearly 0 is also an element of Z. Therefore, we say that identity property is satisfied in Z. So, we have written yes. And coming to the W to test the inverse property. So, take an element 2 belongs to W. 2 plus something is equal to, what is the identity element in W with respect to addition? It is 0. Therefore, 2 plus something is equal to 0. 2 plus something equal to 0. What is this something? This something is, this is minus 2. But this minus 2, is it an element of W? W contains only 0, 1, 2, 3, 4, but no negative numbers. W is not a number or a member of W. Therefore, clearly this inverse property is not satisfied in W. That's why we have written no. Like that, you fill all the rest of the columns. Definitely you have a clear understanding of all these things. So a much more practice is needed by taking different sets and different operations. Thank you all of you for listening to this class. Meet you again in the next class. Thank you very much.